Of all the claims in science, few sound more audacious than this, that we can reconstruct the first 3 minutes of the universe, and much of what came before and after, from a handful of numbers measured today. Yet that is precisely what the hot Big Bang model achieves. It holds that the entire observable universe expanded and cooled from an extraordinarily dense, hot and nearly uniform state some 13.8 billion years ago, and that a small set of measured quantities, the temperature of the relic radiation, the ratio of matter particles to photons, and the present rate of expansion, is enough to predict a whole coherent sequence of physical epochs, each leaving fossils we can still detect. This chapter follows that sequence forward in time, from the unknown physics of the very first instant, through a cooling cascade of transformations, to the moment the universe turned transparent and released the light we now see as the cosmic microwave background. It is one of the great syntheses of modern science. The first thing to understand is what the Big Bang was not. It was not an explosion of matter into a pre-existing void, hurling debris outward from a center. It was, and is, the expansion of space itself, the swelling of the very fabric within which all matter sits, described by the same geometry we met in the previous chapter. Every distance between unbound objects grows in proportion to a single quantity, the scale factor, and light stretches with it, which is why distant galaxies are redshifted. The crucial consequence for cosmic history is that the different contents of the universe thin out at different rates as space expands. Matter simply dilutes with volume, but radiation dilutes faster still, losing an extra measure of energy as every wavelength is stretched. Run the clock backward, therefore, and radiation grows in importance fastest of all, so the early universe was not merely denser but overwhelmingly dominated by radiation, and almost inconceivably hot. 3 independent observations lift this picture from speculation to precision science. The first is the expansion itself, seen in the way galaxies recede in proportion to their distance, which fixes the present expansion rate at about 67.5 kilometers per second for each megaparsec. The second is the cosmic microwave background, an almost perfect thermal glow filling the sky at a temperature of 2.725 degrees above absolute zero, measured with exquisite accuracy by the CODATA satellite, and uniform in every direction to about 1 part in 100,000. It is the cooled relic of the primordial fireball, the light of the hot early universe stretched by the expansion into microwaves. The third pillar is the abundance of the lightest chemical elements, which the model predicts with remarkable accuracy. Together these 3 fix the model's free parameters and let us compute the universe's thermal history with real quantitative confidence, yielding, among much else, an age of 13.8 billion years. The engine that drives the early timeline is a simple and beautiful relationship between time and temperature. In the radiation-dominated era, the rate of expansion is set entirely by the energy of the hot gas of relativistic particles, and this ties the age of the universe directly to its temperature. The hotter it is, the younger it is. The anchor point worth remembering is that when the universe had cooled to a temperature of about 10 billion degrees, an energy of roughly 1 million electron volts, it was almost exactly 1 second old. Earlier than that it was hotter and denser, later cooler and more rarefied, with the temperature falling as the universe expanded. As it cooled, it passed a series of thresholds. Each time, the temperature dropped below the energy locked in the mass of some kind of particle. Those particles could no longer be freely created. They annihilated, poured their energy into the remaining lighter particles, and the bookkeeping of the cosmos stepped down a notch. What happens if we run the clock all the way back toward the beginning? Mathematically, the temperature and density climb without limit, diverging to infinity at time 0, the so-called initial singularity. But this infinity is almost certainly not real. It is a signal that our theory has failed, that Einstein's general relativity, which describes gravity as smooth curved spacetime, has been pushed past its domain of validity. The earliest interval we can even name is the Planck era, the first sliver of time so brief it is written as a decimal point, followed by 43 zeros before the one, when the universe reached a temperature of some 10,000 trillion degrees. At that scale, the quantum uncertainty of spacetime itself becomes overwhelming, and gravity must be combined with quantum mechanics into a theory of quantum gravity that does not yet exist. Candidate frameworks, string theory, loop quantum gravity, remain untested. The Planck era must be flagged plainly as an open frontier, not established science. Just after the Planck era, physicists suspect, lies the grand unification epoch, in which the strong, weak, and electromagnetic forces, so different in our cold world, may merge into a single unified interaction at colossal energies, perhaps 10,000 trillion times higher than the largest particle accelerator can reach. These grand unified theories are elegant and well motivated, but they remain unconfirmed. The slow decay of the proton that they tend to predict has never been observed despite decades of searching. This shadowy early epoch is also the conventional home of two of the deepest unsolved problems in all of physics: the origin of the imbalance between matter and antimatter, and the hypothesized episode of inflation. The honest summary is stark: everything earlier than about a trillionth of a second, before the energies that our accelerators can actually reach, is an extrapolation beyond directly tested physics, and should be read as theoretically structured speculation rather than measured fact. Chief among those early speculations, and the most fruitful, is cosmic inflation, the idea that very early on, the universe underwent a fleeting burst of accelerated, almost exponential expansion, ballooning a tiny patch by a factor of at least 100 trillion in the blink of an unimaginably small instant. Inflation was invented to cure two awkward puzzles of the plain Big Bang. The first is the horizon problem, regions on opposite sides of the sky, which could never have exchanged light or heat nonetheless glow at precisely the same temperature, as if they had once been in intimate contact. Inflation answers that they were before being flung apart. The second is the flatness problem. The geometry of space is observed to be flat to within 0.5%, a balance so precise it would demand impossible fine-tuning unless some mechanism actively drove it there. A brief inflationary stretch does exactly that, smoothing and flattening space and diluting away any unwanted relics in the process. Inflation's most celebrated feature is a prediction almost poetic in its reach: that the largest structures in the universe were seeded by the smallest. Tiny quantum fluctuations in the field driving inflation were stretched to cosmic dimensions and frozen in as gentle ripples in the density of the universe, the seeds from which every galaxy and cluster would later grow. The theory predicts these ripples should be very nearly, but not exactly, the same strength on all scales, and the satellite measurements agree with striking precision, finding just the slight tilt the simplest models require. This is a genuine and impressive success, and yet inflation is not established in the way nucleosynthesis is. The field responsible has never been identified, its behavior is not derived from known physics, and its cleanest signature, a faint background of primordial gravitational waves imprinted on the microwave sky, has not been found. Inflation is best presented as a strongly motivated, observationally encouraged, but not yet confirmed paradigm. As the universe expanded past inflation and cooled, it entered epochs governed by physics we can test in the laboratory. When it had fallen to an energy of about 100 billion electron volts, at around 100th of a billionth of a second old, the electroweak transition occurred. The Higgs field switched on, the carriers of the weak force acquired mass, the photon remained massless, and electromagnetism and the weak force went their separate ways. This is the earliest moment whose energy scale our great accelerators, such as the Large Hadron Collider, actually reach, giving the model a firm experimental anchor. This same era is the favored setting for one of cosmology's profound mysteries: baryogenesis, the origin of the excess of matter over antimatter. For every billion antiparticles in the early universe there were about 1,000,000,001 particles, and when the two annihilated, that tiny surplus became all the matter that exists, every star, every planet, every person. How that imbalance arose is unsolved. The physicist Andrei Sakharov showed in 1967 that generating it from a symmetric start requires three conditions together: processes that violate the conservation of particle number, a preference for matter over antimatter, the laws themselves, and a departure from perfect equilibrium. The Standard Model contains all three ingredients in principle, but far too weakly to explain the surplus we observe, so baryogenesis stands as some of our clearest evidence for physics beyond the Standard Model. Meanwhile, from about a trillionth to a millionth of a second, the universe was a quark epoch. Too hot for quarks to bind, they and the gluons roamed free in a searing quark-gluon plasma. This exotic state is no longer merely theoretical. It has been recreated in collisions at particle accelerators, which revealed that it flows as a nearly perfect liquid. The early universe, briefly, was filled with the most perfect fluid known to physics. As the plasma cooled to a temperature set by the strong force, about 150 million electron volts, some 10 millionths of a second after the beginning, The quarks became permanently confined into the protons, neutrons, and other particles we know today. Careful supercomputer calculations show this quark-hadron transition was not an abrupt change of state, but a smooth crossover. Now the cast of characters for the rest of the story was nearly set. A thin residue of protons and neutrons, the survivors of matter's narrow victory over antimatter, adrift in a bath of photons, electrons, and their ghostly counterparts, the neutrinos. Crucially, protons and neutrons could still transform into one another through the weak interaction, and as long as those reactions kept pace with the expansion, the ratio of neutrons to protons tracked the temperature closely. The neutron is slightly heavier than the proton, so as things cooled, neutrons became progressively rarer, a small imbalance that would soon decide how much helium the universe could make. Around 1 second, at a temperature near 10 billion degrees, the first of the great decouplings occurred. The neutrinos, which interact only through the feeble weak force, found the expanding universe growing too thin for them to keep scattering, and they simply stopped interacting and streamed away freely. They are still out there, a cosmic neutrino background, a sea of relic neutrinos analogous to the microwave background, but released some 380,000 years earlier. We have never detected them directly, for their energies are extraordinarily low, but their presence is demanded and precisely measured by both the microwave background and the abundance of the light elements. Moments later, as the universe cooled below the energy stored in the mass of the electrons and their antiparticles annihilated in a final flash, pouring their warmth into the photons, but not into the already departed neutrinos. That is why the relic neutrinos are predicted to be slightly colder than the microwave background today, one of cosmology's most elegant quantitative results. Now came the universe's brief career as a nuclear furnace. Big Bang nucleosynthesis, the forging of the lightest elements in roughly the first 3 minutes. When the proton-neutron reactions froze out, neutrons were outnumbered about 6 to 1, a ratio that decayed toward 1 in 7 as free neutrons slowly crumbled. Fusion could not begin at once, however, because of a subtle obstacle called the deuterium bottleneck. The first step in building any nucleus is to bind a proton and a neutron into deuterium, a heavy form of hydrogen, but deuterium is fragile, and the universe was still so awash with energetic photons that any deuterium was blasted apart as fast as it formed. Only when the temperature fell to about 1 billion degrees, a couple of minutes in, could deuterium survive, and then fusion raced ahead, sweeping almost every available neutron into helium, the most stable of the light nuclei. The astonishing thing about this calculation is that it hangs on essentially one free number, the ratio of baryons to photons, together with nuclear reaction rates measured in the laboratory. Fix that ratio at the value the microwave background independently requires, and the theory predicts that about 1/4 of all ordinary matter by mass should have emerged from the Big Bang as helium, alongside a whisper of deuterium, a trace of helium-3, and a tiny sprinkling of lithium. Heavier elements could not form because nature provides no stable nucleus of mass 5 or 8 to bridge the gap. Carbon and everything beyond had to await the birth of stars. When astronomers measure the most ancient, unpolluted gas in the cosmos, they find helium and deuterium in just the predicted proportions, confirming the model to within a few percent, that 2 entirely different probes, the light elements forged in the first minutes, and the microwave background released 400 millennia later, agree on the cosmic density of ordinary matter, is among the most compelling consistency checks in all of science. One small discord remains. The model predicts about 3 times more lithium than we actually find in the oldest stars, the so-called lithium problem, and whether the fault lies in the stars, in uncertain nuclear rates, or in some new physics is still unsettled. Setting that aside, the universe now entered a long, quiet interlude. For hundreds of thousands of years it remained a hot, opaque plasma, a glowing fog in which free electrons ceaselessly scattered the photons so that light could travel no distance at all before being deflected. During this stretch, the universe crossed a quiet but pivotal threshold. As it expanded, the density of matter, thinning more slowly than radiation, at last overtook it, and the cosmos passed from being radiation-dominated to matter-dominated. This handover, some tens of thousands of years in, set the stage for gravity to begin assembling structure, though the fog would have to lift before any of it could be seen. The lifting of that fog is the climactic event of the early universe, and it is called recombination. As the temperature fell to a few thousand degrees, it became at last cool enough for protons and electrons to bind together into neutral atoms of hydrogen. Here again the sheer number of photons mattered. There were so many that they kept hydrogen torn apart until well after the naive moment, but once the electrons were finally captured, they vanished from the scene with startling speed, and with the free electrons gone, the photons had nothing left to scatter from. Suddenly the universe became transparent, and the light broke free to travel in straight lines across the cosmos ever after. That release happened about 380,000 years after the beginning, at a redshift of roughly 1100, and that liberated light, stretched more than 1,000-fold by the expansion since, is the microwave background we detect today at 2.7 degrees above absolute zero. It repays care to distinguish three closely related events that popular accounts often blur together. Recombination is the chemistry, the actual forming of neutral atoms, and it unfolds over a span of time. Photon decoupling at a redshift near 1100 is the distinct moment when scattering finally becomes so rare that a typical photon flies free for the last time. This defines the surface of last scattering, the glowing wall that is the earliest thing we can ever see. And a little later comes the baryon drag epoch, when matter is released from the grip of the radiation and free to fall into the gravitational wells of dark matter, an event that stamped a particular scale onto the cosmos, a standard ruler that astronomers still read in the distribution of galaxies today. These fine distinctions, trivial sounding, are the stuff of precision cosmology, computed with dedicated recombination codes to extraordinary accuracy. The microwave background that recombination released is the richest single source of information in all of cosmology. Its near-perfect thermal spectrum confirms that the early universe truly was in hot equilibrium, and imprinted upon its almost uniform glow are minuscule variations in temperature, differences of just 1 part in 100,000, which are at once the seeds of all future galaxies and the frozen echoes of sound waves that rippled through the primordial plasma before it recombined. The precise pattern of those ripples across the sky, the angular sizes and relative heights of their harmonic peaks, encodes the density of ordinary matter, the density of dark matter, the curvature of space, and the rate of expansion. From this single fossil glow, cosmologists have extracted the fundamental numbers of our universe to a precision that would have seemed miraculous a generation ago. Recombination is thus the true horizon of direct observation, the boundary between the opaque universe we can only reconstruct and the transparent one we can actually see. After the light broke free, the universe fell dark. It entered the cosmic dark ages, a cooling expanse of neutral hydrogen and helium and unseen dark matter, with not a single star yet shining. But gravity was patiently at work, drawing matter into the faint overdense ripples the microwave background records, and over hundreds of millions of years, these seeds collapsed into the first stars and galaxies. Their fierce ultraviolet light then flooded outward and reionized the hydrogen gas between the galaxies, ending the dark ages and lighting up the cosmos. Much later still, when the universe was already some 9 or 10 billion years old, a final actor took the stage. The mysterious dark energy, thinning more slowly than anything else, rose to dominate the cosmic budget, and the expansion of the universe, which had been gently slowing for billions of years, began once more to accelerate, the era, confirmed by exploding stars, in which we now live. For all its triumphs, the thermal history of the universe is ringed by deep unknowns, and intellectual honesty demands we name them. The nature of dark matter, roughly a quarter of everything, indispensable to explain galaxies' structure, and the microwave background is simply unknown. No particle of it has ever been caught. Dark energy, more than 2/3 of the cosmic budget and the cause of the accelerating expansion, is even more baffling. The vacuum energy that quantum theory naively predicts overshoots the observed value by a margin so vast it is often called the worst prediction in physics. Inflation remains unconfirmed, and its gravitational wave signature undetected. Baryogenesis has no established mechanism. And a sharp new discord has emerged, the Hubble tension, in which the expansion rate inferred from the early universe stubbornly disagrees, at a level too large to dismiss, with the rate measured directly in the nearby cosmos. It is worth closing by seeing clearly how the certain and the speculative are layered through this story, for conflating them is the commonest error in popular tellings. Everything after roughly the first second, the decoupling of the neutrinos, the forging of the light elements, the release of the microwave background, rests on well-tested physics and agrees with observation to the level of a few percent. Here the model is quantitative and robust. The quark and electroweak epochs rest on physics we probe in colliders but must extrapolate to cosmic conditions. Our confidence is high, but the application is indirect. And the earliest chapters, inflation, baryogenesis, grand unification, the Planck era, are theoretically motivated and sometimes observationally encouraged, yet lack any uniquely confirmed mechanism. A responsible account treats the first second as a frontier of structured hypotheses, and everything after it as established, testable history. That from a mere handful of measured constants we can reconstruct 14 billion years and predict fossils we still detect, is itself a profound clue about the deep order of nature.